Okay, learning goal is to be able to deal with functions in the form of a outside of x minus h all cubed plus k, and these are cubics. So let's go back to what we've just looked at recently. We've considered polynomials. Now if we had a generic cubic in polynomial form, we'd have instead of what you might have seen a to the n, I'm just going to use a, b, c, d, etc. for the coefficients. Okay, you can do that too, they're just the coefficients. So we've got ax cubed plus bx squared plus cx plus d, where a cannot equal 0, and that's a cubic polynomial, and that's in polynomial form. Okay, so we are looking at this other form up here. Now that should ring a bell a little bit because it resembles to a large degree the turning point form of a quadratic, except for we have a different sort of function. We have a cubic and they have quite different properties. So what we can do is, by considering the base function y equals x cubed, we can do transformations on that, just like we did with quadratics. Some of them are very similar too, and if we have it in this other form, which I'm not going to call turning point form because it's a bit more problematic with cubics, although it resembles quadratic turning point form. When we've got it in this form here, if you had something like y equals say 1 outside of x minus 1 all cubed plus 3, just to use an example, we know that that would be translated 1 to the right and 3 up. 3 units up, 1 unit to the right from our base cubic. So let's have a look at some of these transformations, and so that's what we're going to look at now, is transformations of y equals x cubed. So consider the three graphs we have here. We've got y equals x cubed, y equals 3x cubed, and y equals negative 1/2 x cubed. So what we're looking at here is examples of dilation. So we're looking at the coefficient of a there, and these are dilations. So the dilation, like with quadratics, is a shape change. So dilations is a vertical stretch. So this one is dilated by a factor of 1, which means it'll be the same as x cubed. This has a vertical dilation by a factor of 3. So it has a vertical stretch by a factor of 3. All the y values are tripled compared to these ones using the same x values. This one here has been inverted because it has a negative a value, and it has been compressed because its a value is between 0 and 1. So the a value, if it's in that range exclusive, will be a compression, and if it's negative, it'll flip or mirror the graph in the x-axis, or in other words, it'll invert it. So the implied domain and the implied range are both all real numbers, so they can have any real number at all. Okay, what you might notice a bit differently about this, the shape is quite different to the parabola from a quadratic, and we have this flat spot here, and that's a point of horizontal inflection. So horizontal inflection. So the point of horizontal inflection is a point where the gradient equals 0 at one spot. So for your base function y equals x cubed, which is essentially the graph on the left, it'll have the point of inflection at the origin. So it's like an instantaneous flat spot. So you've probably worked out from what we saw before, we have vertical translations and horizontal translations, and that's basically a movement on the plane. It's not a shape change, which we know from quadratics. So basically, if we've got the form x minus h, I'm ignoring the dilation on the front for the moment, and plus k on the outside, that will move h units to the right, just like with quadratics, and k units up. So if that was a plus in there, that'd be minusing a negative, and that would be to the left. So the translations work just like with the quadratics once it's in this form. Note that we don't talk about where the turning point is, we talk about where the point of inflection is. And the point of inflection, just like with the turning point, the point of inflection moves with the translation. So this will move it, the point of horizontal inflection k units up, and this will move the horizontal inflection k units to the right. So it's very much like the turning point behaves with the quadratic, the point of inflection behaves in a similar way with cubics.